All right, let's dive into an organism with a fascinating story, Kingella kingae. This is a bacterium that went from being a footnote in textbooks to a major player in pediatric infections. And the really interesting part? Its story isn't about some new superbug emerging, but about how our own science got better at seeing what was right in front of us the whole time. It's just a perfect case study in how our view of a pathogen can completely flip on its head.
You know, for decades, if you found this organism, it was considered a rare find, a bit of a medical curiosity. But now, well, now we know it's a leading cause of bone and joint infections in young children. So what on earth changed?
This quote really hits the nail on the head. It says, "This was not a true emergence of a novel threat, but rather an unmasking of a prevalent one, driven almost entirely by improvements in laboratory detection methodologies." And that's our theme for today. We weren't facing a new enemy, we just got a much better pair of glasses to find an old one.
Okay, so let's get into the details of this unmasked pathogen. Just a quick heads up, this whole review is a synthesis put together from a Gemini deep search. If you want to see all the primary sources, the citations, all the nitty-gritty details, you can find them in the linked notebook document.
The journey from obscurity to the spotlight is pretty remarkable. It was first described back in the 60s by the great Elizabeth O. King. Then in 76, it got its own genus. But it wasn't really until the 90s that the numbers started to skyrocket, leading to where we are today. Oh, and it's also a member of the HASEC group, that club of fastidious gram-negatives famous for causing endocarditis. That right there is a huge clue about its clinical potential.
So let's build a microbiological profile for this organism. Think of it like we're creating a suspect profile for a very picky and often very tricky foe.
Now here is one of the biggest traps you can fall into right at the start of your investigation. Kingella kingae has this really nasty habit of resisting decolorization in the gram stain. What does that mean? It means this gram-negative bug can show up looking gram-positive or gram-variable, sending your whole identification process down a completely wrong path from the get-go. The single biggest breakthrough in finding Kingella kingae wasn't some complex new machine, it was a simple change in procedure. Before this, trying to grow it from joint fluid was a long shot, with recovery rates less than 10%. But by just taking that fluid and injecting it straight into an aerobic blood culture vial, bam, the recovery rate shot up to nearly 100%. The broth does two things. It gives the bug a great place to grow, and it dilutes out all the stuff that tries to kill it, like antibodies and white blood cells. A true game changer.
So when you get it on the bench, here's what you're looking for. It'll grow in your blood or chocolate agar, but forget about mac and conky. It's a slow grower, so you got to be patient. It likes a CO2-rich atmosphere and might take up to 48 hours or even longer. But the real visual clue, look for that narrow, very distinct zone of beta hemolysis, and keep an eye out for its different colony types, spreading, non-spreading, and domed, which can actually give you clues about its virulence.
All right, so how do we nail the identification? This is the biochemical fingerprint you need. And honestly, the two most critical tests are right there at the top. Kingella kingae is oxidase positive and catalase negative. That combination is your big signpost. It really narrows down the possibilities and points you straight towards your culprit.
Okay, we've got our suspect profiled in the lab. Now, let's move from the microscope to the hospital ward and talk about what's known as the clinical dichotomy of this infection. It's pretty fascinating.
And this is absolutely critical to understand. Kingella kingae has two completely different faces. On one side, you have the most common presentation in kids, a really subtle, mild bone or joint infection. The kid might have a low-grade fever, or no fever at all, and the inflammatory markers are barely elevated. But on the other side, you have infective endocarditis. This is a rare but incredibly severe, aggressive illness that can just tear through heart valves. It's the same bug, but it causes two totally different diseases.
This clinical puzzle is exactly why our diagnostic tools had to get better. So let's take a look at the modern arsenal we have now to unmask this thing faster and more reliably.
Culture is great. It's the gold standard, but nucleic acid amplification tests, or NATs, have been a complete game changer here. A real-time PCR targeting the RTX toxin gene is way more sensitive and gives you an answer in hours, not days. It's super versatile, too. You can use it on joint fluid, blood, even tissue blocks. But, and this is a big but, it does have a key limitation. It cross-reacts with the very rare Kingella negavensis. Because of this, your report must state that Kingella kingae / negavensis DNA was detected. That's a critical reporting nuance.
So, once we've found it, how do we fight it? Let's break down its unique antimicrobial profile, because it has a few surprises up its sleeve.
For anyone involved in guiding therapy, this slide is non-negotiable. First off, Kingae is intrinsically resistant to vancomycin. The drug molecule is just too big to get through its outer membrane. It's also frequently resistant to clindamycin, which is a key point we'll come back to. And crucially, some strains have picked up a beta-lactamase, making them resistant to basic penicillins. The kicker, the percentage of these resistant strains changes massively depending on where you are in the world.
So to make sure we're all speaking the same language when it comes to susceptibility, we turn to EUCAST, the European Committee on Antimicrobial Susceptibility Testing. These are the official clinical breakpoints as of 2024. This is the definitive rulebook for interpreting your results, whether you're running MICs or just looking at disc zones, and for making sure you're guiding therapy correctly.
And this is where things get really interesting, a direct conflict in the clinical guidelines. The international guidelines from the IDSA and PIDS are pretty straightforward. But then you look at the Dutch Pediatric Association, the NVK guideline. For the oral switch, it lists clindamycin as a second-choice agent. This flies directly in the face of the microbiology we just talked about, where we know this organism is very often resistant to clindamycin. So this brings us to a really important question for everyone working in the lab. What is your role when the official guidelines and the hard microbiological data don't line up? The answer is simple. Your role is to be more than just a technician. You're a consultant. It is absolutely essential to pick up the phone and communicate this pathogen-specific data to the clinicians to help them avoid a potential treatment failure.
Finally, let's zoom out a bit and look at the public health picture. How do we go about containing an outbreak of Kingella Kingae?
The epicenter for Kingella Kingae outbreaks is almost always daycare centers. It spreads from person to person through respiratory secretions, and these outbreaks are usually driven by a single, highly virulent clone that just rips through the facility. So the key takeaway for public health and for clinicians is this: a single invasive case in a child who attends daycare should be a huge red flag that triggers a much higher level of vigilance for more cases.
So, if we had to boil this entire story down to one powerful central message, it would be this. The lesson of Kingella Kingae is that diagnostic yield is dynamically linked to laboratory methodology. It's an incredible reminder of how an innovation in the lab, even a simple one, can completely change our understanding of a disease.
And that leaves us with one final, kind of unsettling question to think about. If a simple procedural change like using a blood culture bottle could unmask a major pathogen like this, what other pathogens are we missing right now? What else is out there, hidden in plain sight, just waiting for the right test to finally find it?
The story of Kingella Kingae really is a powerful reminder of what still might be hidden from us. What do you think? Have you ever run into similar diagnostic puzzles in your own lab? Let us know and share your experiences in the comments below. And hey, if you found this explainer useful, please subscribe for more deep dives into the incredible world of microbiology.